So at long last, we're done with our overview, and now we're going to talk about evaluating the concurrency and parallelism mechanisms we've talked about thus far. And the tricky thing here is I've just given you a summary of a boatload of things. And so an obvious question is, when should I apply any of those different things? Well, the very pragmatic answer in this class is you apply the things that come along with the programming assignments. So that's the very pragmatic answer. But that's not a good answer in practice. You should know the reasons why we would choose one thing versus another. So first thing to note, Java's concurrency and parallelism mechanisms span multiple layers in common software stacks, platforms. This is sort of it's kind of the Android stack, but if you looked at iOS, you'd see a similar stack. If you looked at Linux and abstractions on Linux, you'd see a similar stack. So this is by no means just related to Android or Java. But Java's concurrency and parallelism mechanisms span multiple levels. You can see here there's some things that take place in the operating system, like operating system kernel threads. There's some things that take place in system libraries, things like programming the POSIX pthreads abstractions, which is a threading model for C programmers. Then there's also various execution environments, things like virtual machines or execution runtime-based or compile-time-based execution environments. There's also concurrency and parallelism frameworks that are going to be things that are provided as libraries that live atop the underlying execution environment. And then there's also application frameworks that are on top of all that. And finally, the applications that sit at the very tip of the iceberg here. And so there's lots of different places to choose from. And a good question is, why would you make a choice at any one layer or layers versus another? And as it so often turns out, choosing the right mechanisms depends on different factors. And part of the job of becoming a good software developer, especially if you want to keep going up the technical ladder, to become an architect or a lead, you need to be able to make choices about the alternatives and make them informed so you can convince your colleagues and your customers and your bosses and so on that you're doing a good job. So if you're trying to build low-level stuff, let's say you're trying to build performance-sensitive apps, like maybe a gaming platform might be a good example of, or gaming application of a performance-sensitive app, or something that's going to be doing processing of data in a hospital environment where you need to get answers quickly because lives could be at stake and so on and so forth. So you might prefer to use the really low-level shared object mechanisms available in the package Java Util Concurrent, and more specifically, Java Util Concurrent locks. So reentrant locks, semaphores, things like condition objects, stamp blocks, and so on and so forth. Those are mostly things we're not going to cover in this class, but if you were interested about that, you could go watch a video here and you'd learn all about that. The good part about using those low-level synchronizers is they're very efficient and lightweight because they don't do a whole lot, so they're meant to be lightweight. But because they are lightweight and don't do a whole lot, they tend to be somewhat tedious and error-prone to use in practice. So I would typically recommend using this level, the shared objects, synchronizers, and so on, if you're building infrastructure stuff. You're building the Java platform, or you're building the Android platform, as opposed to using the Android platform or using the Java platform to build higher-level applications. This is not uncommon. People often use lower-level primitives to build infrastructures. Now, there's another model we talked about briefly called message passing, and that's where you communicate using various synchronized queues or thread-safe queues or bounded buffers and so on. Things like array blocking queue, linked blocking queue, synchronous queue, and so on. There's a whole slew of them as well in Java and Android. And if you're building frameworks as opposed to lower-level infrastructure, that might be something where message passing mechanisms are used. So Android, for example, has this interesting framework called handlers, messages, and runnables, which I call the hammer framework. Show it with Thor's mighty hammer. So if you're the Android developers and you're building the hammer framework, you might want to use message queues to communicate between producers and consumers of events in the Android system. And Java itself has a bunch of frameworks that come out of the Java 5 era, such as the executor service and executor completion service. And those are also based on thread-safe queues to take data from clients and then submit them to a pool of threads where they're processed and the results come out at some later point in time. So frameworks can be useful if you're building frameworks for reuse, message passing is a very common approach. The good news with message passing is it's fairly flexible and decoupled. You separate producers and consumers in time and space, which is nice. But the downside is that passing messages between threads has some additional overhead. So you have context switching overhead, synchronization overhead, data movement overhead, and so on and so forth, and synchronization overhead. So they tend not to be quite as fast as the shared object synchronizer approach we talked about before. So these are the things that can be a little bit higher cost. But a lot of times it doesn't matter because you're not trying to get every last nanosecond of the system. You're trying to make it easier for people to program. You're looking at the productivity side of the house. There are also these other higher level frameworks. So parallel streams, completable futures, Project Reactor, RX Java, the reactive stream stuff we talked about. And those are most useful for people building apps. So if you're an app developer building an Android app or some other kind of app, then these higher level abstractions are probably what you want to go with, just because they will give you plenty of performance with much better productivity once you've popped into the programming abstractions that they're offering. So the good news is they make you very productive. They abstract away from a lot of accidental complexities that you can run into, things like race conditions for forgetting to lock things, or memory inconsistencies, and so on and so forth. So that's all good. The downside is, again, they're abstracting things away, so there will be some overhead. Those abstractions don't come for free. And if your problem doesn't fit into what they're trying to do, you end up with this Procrustean bed. If you're familiar with the myth of Procrustes from Greek mythology, where Procrustes was an innkeeper, and he offered travelers this great deal. He'd say, you can stay in my inn for the night and sleep for free. But the problem was, if you didn't fit into his Procrustean bed, he would either stretch you till you fit or chop you up until you fit. So that's what people talk about as a Procrustean bed. It sometimes means that you're not getting all the benefit you think because you're getting a penalty by having to fit into some rigid constraints. But as a general rule, the higher level stuff is where it's at. And that, of course, is what we're going to focus on in this course. Now, people who aspire to the exalted moniker of full stack developer should be fluent with every layer. A full stack developer is someone who's able to program throughout the stack. Now, there are not that many people who do that, but if you're able to do that, it gives you an edge when you're competing with other people for a programming project, or trying to get a raise, or trying to go to work at the dream company of your choice. The more you know about the whole stack, the better off you'll be. And a lot of times, nowadays, people have lost the knowledge of how these lower layers work. And in fact, it's kind of fascinating just thinking about what we teach in a modern computer science degree program. If you had been here 20 years ago, we would have focused on a lot more lower level stuff. Necessarily, there wasn't a lot of the higher level stuff. And people spend a lot more time on those nitty-gritty nuts and bolts things like operating system kernel programming or something. Very, very few of you will ever go do operating system kernel programming. It might help to know a little bit about it, just like it might help to know a little bit about assembly programming, but you're very, very unlikely to ever do any of that anymore. So the world keeps raising the level of abstraction, but it helps to know other older things as well. Regardless of which mechanisms you select, be it concurrency, parallel, message passing, shared objects, application frameworks, be prepared to address and master the accidental and inherent complexities in whatever layer or layers you choose. And there's a great quote here. You've probably seen this meme before, but this is a funny one for this class. Whoever said the definition of insanity is doing the same thing over and over again, but expecting different results, wasn't debugging concurrency issues. Change my mind. So this is pretty funny, because oftentimes what you'll get when you have concurrent programs with bugs in your concurrent programs is you'll run them over and over again, and you'll get different results each time. And it's not it'll drive you insane. It's not because you're insane. It'll drive you insane. But it's a good example of what makes this particular area so tricky, because behaviors differ depending on different contexts. If you're in the debugger, you're not in the debugger. If you have N processors versus M processors, what kind of a workload you're doing, what the phase of the moon is, did you throw salt over your shoulder, whatever, you're going to get different behaviors. Okay, so that is the end of our introductory section on concurrency and parallelism. focusing on Java.